An electrical panel labeled as 208Y/120V 3-phase full wire is observed to be fed with 120/240 single-phase power. This discrepancy between the labeling and the actual power supply is the first point to consider. The panel is fed with 4 sets of 500 kc mil copper conductors. This is a substantial amount of copper for a 1200 amp panel. The conductors originate from a CT cabinet, which has one 3-inch conduit coming from the transformer. It is suspected that there is one set of 350 kc mil aluminum conductors within that 3-inch conduit. Let's analyze these observations to understand possible reasons for this configuration. Firstly, a panel is fed with single-phase power, not 3-phase power as indicated on its label. This mismatch is significant and should be investigated further. Secondly, the feeder cables are 4 sets of 500 kc mil copper, which is significantly oversized for a 1200 amp panel. This oversizing raises questions about the original design intent. Thirdly, the CT cabinet has one 3-inch conduit coming in from the transformer, which is likely carrying a single set of 350 kc mil aluminum conductors. This suggests a potential mismatch between the transformer's output and the panel's feeder. Let's examine possible explanations for these observations. One explanation is that the oversized feeder cables could have been installed in anticipation of future expansion of the electrical system at the Marina. This would allow for additional load to be added without having to upgrade the feeder cables. This is a common practice to save on future labor and material costs. Another possibility is that the original feeder cables were damaged or undersized and were replaced with the current oversized cables. However, this would be an unusual practice, as the original cable should have been sized appropriately for the panel's capacity. If the original cables were indeed undersized, it indicates a potential design flaw or a change in the load requirements after the initial installation. Another explanation is that the panel may have been mislabeled as a 3-phase panel when it is actually a single-phase panel. This could be a manufacturer error or an error in the installation process. Mislabeling can lead to confusion and potentially unsafe conditions. The oversized feeder cables may provide an additional safety margin for the electrical system. In the event of a fault, the cables would be able to carry the increased current for a longer period of time, reducing the risk of damage to the panel or other equipment. This is a conservative approach to electrical design, but it can be more costly due to the increased material requirements. Regarding the single set of 350 kc mil aluminum conductors in the 3-inch conduit, it is possible that the transformer is a single-phase transformer and only requires 3 conductors, which are 2 phases and a neutral. This would be consistent with the single-phase power being supplied to the panel. It is also possible that the conduit has been derated due to the number of conductors, 4 sets of 500 kc mil copper, reducing the allowable ampacity of the aluminum conductors. When multiple conductors are installed in a conduit, the heat generated by each conductor can raise the overall temperature within the conduit. This increased temperature reduces the ampacity of the conductors, requiring a derating factor to be applied. Now let's delve deeper into the technical aspects of these observations. The fact that the panel is labeled 208Y/120V 3-phase but is fed with 120/240 single-phase is a significant red flag. A 208Y/120V system is a 3-phase 4-wire system typically derived from a Y-connected transformer. In this configuration, the voltage between any 2 phases is 208 volts, and the voltage from any phase to neutral is 120 volts. Supplying single-phase power to a panel designed for 3-phase power can lead to several issues. Firstly, the loads connected to the panel may not operate correctly as they are designed to be powered by 3-phase voltage. Secondly, a panel's circuit breakers and other components may not be properly rated for the single-phase voltage, potentially leading to overloads or other problems. The use of 4 sets of 500 kc mil copper conductors for a 1200 amp panel is highly unusual. According to the National Electrical Code, ORNEC, Table 310.16, 500 kc mil copper conductors with a 75°C insulation rating have an ampacity of 380 amps. 4 sets of these conductors would provide a total ampacity of 1320 amps, which is significantly higher than the panel's 1200 amp rating. This oversizing could be due to several factors, including future expansion, voltage drop considerations, or a desire to reduce conductor temperature. However, it is important to note that oversizing conductors does not necessarily improve the safety of the electrical system. In fact, it can sometimes create new problems, such as increased cost and difficulty in working with the larger conductors. The presence of a single 3-inch conduit from the transformer to the CT cabinet suggests that the transformer is relatively close to the panel. The fact that this conduit is likely carrying a single set of 350 kcmil aluminum conductors raises questions about the transformer's capacity and the overall design of the electrical system. According to NEC Table 310.16, 350 kcmil aluminum conductors with a 75 degrees Celsius insulation rating have an ampacity of 250 amps. If this is the only set of conductors feeding the panel, it would be significantly undersized for a 1200 amp panel. However, it is possible that the transformer is not directly feeding the panel, but rather feeding the CT cabinet, which then distributes power to the panel via the 4 sets of 500 kcmil copper conductors. In this case, the 350 kcmil aluminum conductors would only need to be sized to carry the current required by the CT cabinet, which may be less than 1200 amps. Now let's discuss the possible explanations in more detail. The explanation that the oversized feeder cables were installed in anticipation of future expansion is a plausible one. Marinas often experience growth in demand as new boats are added or existing boats are upgraded with more electrical equipment. Installing oversized feeder cables upfront can save time and money in the long run by avoiding the need to replace the cables later. However, it is important to ensure that the panel and other components are also rated for the increased load. The explanation that the original feeder cables were damaged or undersized is less likely, but still possible. If the original cables were damaged, it would be more cost-effective to simply replace them with cables of the same size. If the original cables were undersized, it would indicate a design flaw or a change in the load requirements after the initial installation. In the other case, it is important to correct the problem by installing properly sized cables. The explanation that the panel may have been mislabeled is a serious concern. If the panel is indeed a single-phase panel, it should be labeled as such. Mislabeling can lead to confusion and potentially unsafe conditions, especially for electricians who are unfamiliar with the electrical system. It is important to correct the mislabeling as soon as possible. The explanation that the oversized feeder cables provide an additional safety margin is a valid one, but it is important to note that oversizing conductors does not necessarily improve the safety of the electrical system. In fact, it can sometimes create new problems, such as increased cost and difficulty in working with the larger conductors. It is important to design the electrical system to meet the minimum requirements of the NEC and then at a reasonable safety margin. Regarding the single set of 350 kcmil aluminum conductors in the 3-inch conduit, the explanation that the transformer is a single-phase transformer is consistent with the single-phase power being supplied to the panel. In this case, the 350 kcmil aluminum conductors would only need to be sized to carry the current required by the transformer. The explanation that the conduit has been derated due to the number of conductors is also possible. When multiple conductors are installed in a conduit, the heat generated by each conductor can raise the overall temperature within the conduit. This increased temperature reduces the ampacity of the conductors, requiring a derating factor to be applied. According to NEC Table 310.15b3, when there are more than 3 current-carrying conductors in a conduit, the ampacity of the conductors must be reduced. The amount of the reduction depends on the number of conductors and the ambient temperature. In this case, with 4 sets of 500 kcmil copper conductors in the same conduit as the 350 kcmil aluminum conductors, the derating factor could be significant. Now, let's consider the implications of these observations for the safety and compliance of the electrical system at the marina. The most concerning issue is the mismatch between the panel's labeling and the actual power supply. If the panel is indeed a three-phase panel, but is being fed with single-phase power, it is likely that the loads connected to the panel are not operating correctly. This could lead to equipment damage, overheating, or even electrical fires. It is essential to correct this problem by either supplying the panel with three-phase power or replacing the panel with a single-phase panel. The oversized feeder cables are not necessarily a safety hazard, but they do represent an unnecessary expense. If the cables were installed in anticipation of future expansion, it is important to ensure that the panel and other components are also rated for the increased load. If the cables were installed as a safety margin, it is important to ensure that the design meets the minimum requirements of the NEC. The single set of 350 kcmil aluminum conductors in the 3-inch conduit could be a safety hazard if they are undersized for the load they are serving. It is important to verify the ampacity of the conductors and ensure that they are properly protected by circuit breakers or fuses. The derating of the conduit due to the number of conductors could also be a safety hazard if it is not properly accounted for. It is important to calculate the derating factor and ensure that the conductors are sized appropriately. Given these observations and potential issues, it is advisable to have the electrical system at the Marina inspected by a qualified electrician to verify its condition and correct any potential problems. The electrician should be able to determine the actual configuration of the electrical system, identify any safety hazards, and recommend corrective actions. The inspection should include a thorough review of the panel labeling, the feeder cable sizing, the conduit fill, and the transformer capacity. The electrician should also verify that the electrical system meets the minimum requirements of the NEC and other applicable codes and standards. In addition to the safety and compliance aspects, it is also important to consider the efficiency and reliability of the electrical system. Oversized feeder cables can reduce voltage drop and improve the efficiency of the system, but they also increase the cost. Undersized conductors can lead to voltage drop and overheating, which can reduce the reliability of the system. It is important to design the electrical system to balance cost, efficiency, and reliability. Regular maintenance and testing of the electrical system can also help to improve its reliability and prevent problems. This includes inspecting the panel for signs of corrosion or damage, testing the circuit breakers and fuses, and tightening the connections. In conclusion, the electrical system at the Marina presents several unusual features that warrant further investigation. The mismatch between the panel's labeling and the actual power supply, the oversized feeder cables, and the single set of 350 kcmil aluminum conductors in the 3-inch conduit all raise questions about the design and installation of the electrical system. A thorough inspection by a qualified electrician is recommended to ensure the safety, compliance, efficiency, and reliability of the electrical system. This inspection should include verifying the panel labeling, the feeder cable sizing, the conduit fill, and the transformer capacity, as well as ensuring that the electrical system meets the minimum requirements of the NEC and other applicable codes and standards. By addressing these issues, the Marina can ensure the safe and reliable operation of its electrical system for years to come. Remember, electrical work should always be performed by qualified professionals to ensure safety and compliance with applicable codes.